Just wanted to do a little recap of the big theorems that we got to know for the AP test, as well as go through a little bit of the important stuff in this blue packet right there. But the extreme value theorem isn't anything major that you like have to do calculations with. It's just you have to know if you have any continuous function on a closed interval, it will guarantee to have both a maximum and a minimum value right there. So if it doesn't have both a max or minimum value, that means it's not a continuous function. But if it's continuous and you got closed interval, you have to have a high point, you have to have a low point, guaranteed to have it. That's your extreme value theorem. Now the other theorems, the intermediate value theorem, we did this in chapter 1. So it just says you got to have continuous and you got two different y values. Let me just do a little recap right here. So the intermediate value theorem, it just means like if you have a continuous function, I'm not allowed to lift up the pen when I draw that thing. If you have a y value down here at 2 and a y value up here at 5, you have to cross through all the y values in between. So if it says, gives me some sort of info and then says, show that the y value has to be equal to 4, I would probably like plug in my endpoints at some point, say, hey, here I have a y value of 2, here I have a y value of 5, 4 is in between the 2 and the 5. And then I jot down IVT. IVT guaranteed that the y value has to cross through all that stuff in between right there. So if I ever have to like involve anything that's showing that the y value is equal to a number, I'm usually just gonna jot down IVT, and that's like a big deal right there. And then the other one, Rolle's theorem, just simply says, it says you got a continuous and a differentiable function. So it'll always say continuous on the closed interval, differentiable on the open interval, because remember, something's not differentiable at the endpoints and at the corner points. But Rolle's theorem says if you have f of a is equal to f of b, which means if you have two y values that are the same, like here I have two dots where the y values are both equal to 3, it says if you got a continuous differentiable function, means it's smooth and curvy, can't lift up your pencil, and you got, you know, to get from this y value back to that same y value, you had to turn around and go back in that same direction. So you had to go turn around. And so that point where you turned around, that's where your graph leveled off. And you got a horizontal tangent line right there. The slope is equal to 0. The derivative is equal to 0. So Rolle's theorem always involves showing that the derivative is equal to 0 right there. And then the mean value theorem, that says if you got a continuous and differentiable function, at some point the derivative is equal to this average rate of change right there. So if you just have a smooth and curvy curve, all right, if I do like, hey, this is a comma f of a, and this is the point b comma f of b, if I just did the slope of that secant line right there, the slope of that dashed line, then that would just be your slope formula, your f of b minus f of a over b minus a, right? That's like your average rate of change from this point to this point. But see, if I say what's the instantaneous rate of change right there at x equals c, that would be like, what is my derivative equal to? So right there, the slope of that pink line, that would be my derivative, that instantaneous rate of change. So at some point, the instantaneous rate of change is equal to the average rate of change right there. So the mean value theorem always involves taking the derivative and having it equal to a number. So those are like the big things I kind of remember. If I have to like, if they say explain why the y value is equal to something, or I have to show that the y value is equal to something, or something is in between two other things, I jot down intermediate value theorem. If I see anything involving the derivative setting equal to 0, I'm thinking Rolle's theorem. If I see anything where the derivative is equal to a number, you know, like other than 0, like if it's 0, it's Rolle's theorem, it's equal to another number, then that's my mean value theorem. So that's just a little recap. And then as we see theorem type problems in the free response or in the multiple choice, we'll talk about those some more. I just want to give you a brief recap. And then I'm done talking about the theorems. I'm just going to talk a few seconds now about just some other important stuff in the blue packets. Make sure you study and you really familiarize yourself with everything that's in it. I think the blue packets, your calculus summary things, is going to be the most beneficial thing for you. There's some good stuff in that green packet as well. You could look through there. But as you get stuck on something, we keep referring to a lot of this stuff in here, just a summarize of all your limit stuff, when you're going to use a L'Hopital's rule, talking about the 3.1 absolute extrema problem that we keep using on the word problems there, where you're checking the endpoints and the critical numbers, and then how to justify it if it's a max or min. You know, if it's asking for the max or min, it wants the y value. If it says where's the max or min occur at, it wants the x value, and how to justify if it's a relative max or min. If it's a relative max, if your f prime changes from positive to negative, f has a relative min if your f prime changes from negative to positive. So there's some real good things in there. And then the second derivative test, we've used that a few times as well. We're going to use that quite a bit in the free response and the multiple choice. But if they ever have you find the second derivative and turn right around and ask, is that a max or min or neither, then they're meaning for us to do that second derivative test right there. Where if your first derivative is 0, that means your graph level is off. And if your second derivative is positive or negative, that means your graph is concave up or concave down, creating a low point in that area for a min or a high point in that area for a max there, okay? I mentioned about the inflection points. We know it goes position, velocity, acceleration when you're doing the derivative and doing an integral. And then something that occurs on the AB like all the time is like speed is increasing if speed and acceleration have the same sign. Speed is decreasing if speed and if the velocity, speed is increasing if velocity and acceleration have the same sign. Speed is decreasing if velocity and acceleration have opposite signs right there. Speed is always the absolute value of velocity. And on those graphs where you got like the first derivative, second derivative, stuff like that, sometimes we get confused of, I don't know whether I'm supposed to look at whether it's going above to below the x-axis or if we're going uphill to going downhill. So this little chart is kind of meant to do that. Like increasing means something's going uphill, decreasing means something's going downhill. If I tell you that something is positive, whether that's the second derivative graph or the 14th derivative graph, if I tell you that thing is positive, it means that thing is above the x-axis. Or if I tell you like the 35th derivative graph is negative, that means that 35th derivative graph is below the x-axis. So we know if our function is increasing, our derivative is positive. That would mean our derivative graph is above the x-axis. Our original function graph is going uphill. If our function is decreasing, our original graph is going downhill, but our derivative would be negative because it has negative slopes, which means the derivative graph would be below the x-axis right there. If you have a max or min, you know that's where your first derivative is going to be 0. If you got the possible inflection points, that's where your second derivative is 0. But to be a max or min, your first derivative has to change sign from plus to minus or minus to plus. To be an inflection point, your second derivative has to change sign from plus to minus or minus to plus. And if your original graph is holding the water, then your second derivative is going to be positive, right? If your original graph is spilling the water, concave down, then your second derivative is going to be negative right there. And then just your derivative graph would be increasing, your derivative graph would be decreasing right there. But we'll talk about some of those things as we go forward. But just kind of keep that in mind a little bit. But we'll just really need to get practice with those and then group those problems together and then study those and make sure we got those like sharp in our head there. So that's a bunch of stuff on the first page. We got the area formula for a trapezoid if we need it, the Riemann sum is involving the rectangles if we need there. It's got your disk method, review, shell method. Probably not on that AP test there, but it's going to be the disk method and your areas, your top curve minus your bottom curve type of stuff there. Cross sections, I give you some formulas that we might want to be familiar with. A lot of times they give us formulas, but sometimes they don't. So I would be familiar with some of those there. It gives you the steps there. Solving the differential equation process. Hey, integrate both sides. Remember your plus c. Use the point they give you, the initial condition to find your c value. Plug that back in, and then you got your equation. Derivative is area. I'm sorry, derivative is slope. Integral is area. We talked about the theorems, your definition of continuity. You have to have a y value, have a limit, and the limit is equal to the y value. And we got your average value formula, your average rate of change. We got your cloud stuff from your increasing, decreasing, concave up, concave down. We have a separate video talking about the second fundamental theorem of calculus and your derivative of the inverse. We got the L'Hopital's rule there. And then just on this side here, we haven't seen any yet, but they will eventually give it. We will eventually see some problems where we have to do the notation. These will be really easy for us, but the first time you see it, you might just need a refresher. But there's how you do your product rule. That's just your first times rule, the second plus the second times rule, the first. So when we see the notation problems, here's your product rule, here's your quotient rule, chain rule, do the derivative of the outside function, leave the inside function alone, times it by the derivative of the inside function, and here's a power. You multiply by the power, leave the inside alone, decrease the power by 1, times it by the derivative of the inside. We'll have some more practice with those. That'll be in the multiple choice and the free response stuff right there. The main definition, I think we probably just be familiar with that just in case. I've never seen the main definition of the integral. That's not going to be on the AP test. Neither is Newton's method or trapezoidal rule or Simpson's rule. I've never seen those on the AP test as well. This growth and decay formula, sometimes we might need to worry about that. That's like the initial amount, and then that's the time period, and that's like the rate that something's kind of changing there. And then this stuff is just some stuff that it says stuff you must know code. It means you should have like your trig derivatives memorized, right? This stuff is for everybody. Just if it has a star next to it, that's only a BC topic. Like all this stuff with like the parametric stuff and arc length and Taylor-Maclaurin series, all those star things, those are just for the BC test. And then the last sheet just gives us, it stresses to, hey, show your work. They're interested in your work there all the time. And also it tells us the top 10 student errors. Like sometimes when students see the second derivative is equal to 0, they want to say that's an inflection point. That's wrong. There has to be an inflection point if the second derivative changes sign from plus to minus or minus to plus right there. Sometimes when people see 1 over something, they want to say that's the ln right away. We know all year, like it has to be 1 over a single letter. Like if you got 1 over x cubed, you make that x to the -3 and you integrate that, you go x to the -2 over -2, and then you could do your plus c and get rid of your negative exponents. They're treated like a normal integral. But if it's 1 over a single letter, then it's going to be an ln right there. So we're not going to make that mistake there. But just look through that blue sheet, really study those things. I think that'll be the most beneficial thing for us. Instead of trying to dig up everything in your old notes and stuff from a long time ago, there's a lot of really helpful information in there. And I'll keep referring to that as we go through our problems there. Buffalo Bills